Hello and welcome to a video on the fundamentals of linear regression. Today we're going to be looking at a scenario about how much fuel a train will need. So we've got the Great Plains Railroad is interested in studying how fuel consumption is related to the number of rail cars for its trains on a certain route between Oklahoma City and Omaha. So here we have 10 trains with a various number of rail cars. And we have the fuel consumption in units per mile that was needed for each train. Notice it makes sense that we're plotting the number of rail cars on the x-axis and the fuel consumption on the y-axis. That's because in this scenario, we're measuring how much fuel the train needs, and we're wondering, does the number of rail cars explain the variation in fuel consumption? Also here, I've listed a residual plot, and you probably don't know what a residual is yet, so just sit tight and you will learn that in this video. So let's get some vocabulary out of the way. First, the variable that we're going to plot on the x-axis, it's called the explanatory variable. It's a quantitative variable, and in this case, we're wondering if increasing the number of rail cars has anything to do with the amount of fuel the train needs. We're wondering if the number of rail cars helps explain the variation in the fuel. The response variable, this is the variable that we're interested in measuring. So in this case, it's the fuel consumption for the train. The variable that we're interested in measuring, the response, we are always going to plot that on the y-axis. There are three main features that you want to look for when you're looking at a scatter plot of bivariate data. The first is, do the data points have any particular shape? Does the relationship appear to be linear or nonlinear? Is there any relationship at all, or is there a random scattering of points? I would say in this case it looks like we have a linear relationship. The direction. Do the points seem to be increasing or decreasing? Does there seem to be a positive or negative slope? In this case, we have an increasing relationship. And lastly, you want to think about the strength of your relationship. Does the relationship appear to be weak, moderate, or strong? Now this is a value judgment, but I would say that in this case the relationship appears to be quite strong, because if we visualize a trend line being plotted through the points would probably fall fairly close to the trend line. So if we wanted to talk about all of that in context, we could say there's a strong linear and positive association. As the number of rail cars is increasing, the fuel consumption is increasing as well. Let's just look at a few quick examples before we get back to talking about our trains. So you might want to pause the video and see if you could describe these three relationships. So the first, I would say that as the driver age increases, the sign legibility distance decreases. It looks like we have a moderate, linear, and negative association. Now I'm saying that relationship is moderate because if we plotted a trend line through those data points, I mean, it does look like those points follow a linear trend, but it does look like there's some variation. Not all the points are going to be really close to the trend line. So I'm going to say that that's moderate. Notice there is a bit of a value judgment here. In this second example, this relationship definitely looks very strong, but also nonlinear. So I would say that there's a strong nonlinear association. As the speed increases from 0 to about 60 kilometers per hour, the fuel used decreases, but as speed increases from 60 kilometers per hour, the fuel then increases. So that looks like a very strong but nonlinear relationship. And in this third example, it looks like there's no relationship at all. The data is randomly scattered. There's no association between height and head circumference. So let's pop back to talking about our trains and rail cars here. You'll need to have a strong understanding of how to use all of the linear regression functions on your calculator. So let's go through that now. The first thing you'll want to be able to do is put data into lists in your calculator. So if you hit the Stat button and then go into the Edit, you can put data in any of the lists you want. I'm going to put the explanatory data in list 1. Alright, I have my explanatory data in list 1 and my response data in list 2. Now, I'm going to hit second in mode to just quit back to the home screen. I'm going to perform a linear regression. So I'm going to hit the Stat key, then I'm going to go to Calculate, or Calc, that's the middle option, and I'm going to choose linear regression. Now on my calculator, that's option 4. On your calculator, that might be a different option, so you've just got to be careful. Now, another thing to notice is that once you hit that button, depending on the model of the calculator you have, the screen that you see right now may be different. So I have one of the older models simulated here on my computer. So I have to know that the series of inputs that I need is I need to type in the explanatory list, which in my case was L1, so I hit second and then 1, comma, the response list, comma, and then I want the calculator to input the regression equation directly into a function in the calculator that's going to graph it. So I'm going to hit vars and go to y variables and function, which is option 1, and choose y1. So my regression equation will automatically be stored in y1 in the calculator. Then I'm going to hit enter. Now, you might not have that menu. Your calculator might ask you for the x list, the y list, and where you want the regression equation stored, and then in those spaces you can just put list 1, list 2, and y1 respectively. Also, it's worth noting that you don't have to use list 1 and list 2. You could put the data in any of the lists you want. Just make sure that you key in the appropriate lists at the appropriate times, depending on where you stored the data. Now, we sort of have a problem here because I would like the calculator to display the correlation coefficient and the coefficient of determination, and we'll talk about what those are in a moment. But we need to turn that option on the calculator. So if you're not having r and r squared displayed, as I am not, you have to go into the catalog, which is second 0. Alpha lock is on, so I hit the D key, which is x inverse on my calculator. So I could scroll quickly down to the D functions, and I'm going to turn my diagnostics on. Now once diagnostics are turned on, I don't need to turn them on again unless the RAM is cleared on my calculator or my calculator is reset for some reason. So it's worth remembering where the diagnostics are in case you need to turn them back on again. Now I just need to run the regression again. And when I run the regression again, now the calculator tells me r and r squared, and we'll talk about what those are in a moment. Now, make sure you pay close attention to what the letters are in your calculator. In my case, A is the slope, so my slope is 2.1495, and my y-intercept is 10.6768. So just to recap, you want to be able to put data in lists, choose linear regression from that Stat Calc menu, make sure that you type in the correct lists and you know how to select y1 from the vars menu, and then you will get the output from your linear regression. And if you are not seeing the coefficient of determination r squared and the correlation coefficient r, make sure you remember that if you hit second 0, you can go into the catalog and you can scroll down and turn your diagnostics on. And then when you rerun your regression, you will see r and r squared. So this screen just serves as a handy series of reminders. Now let's interpret that regression equation. So here I've written the regression equation, but I've defined the variables right in my equation. So instead of saying y equals 2.1495x plus 10.677, I've replaced x with railcars, because that's what x is in this problem, and I've replaced y with fuel hat. Now, why have I written fuel as fuel hat? Well, that's because the regression equation does not tell me how much fuel a train needed with a particular number of railcars. It provides me a prediction for how much fuel a train will need with a particular number of railcars. Let's talk about what the slope and the y-intercept actually mean. My slope in this case is 2.1495 over 1. But what are the units on my slope? So the units on the slope will be the units for the response divided by the units for the explanatory variable. So in this case, the units for my slope will be units per mile, since that's the units for fuel, over number of railcars, since that's the units on the explanatory variable. So what this slope actually means is that for every one additional railcar, the model predicts the train will need 2.1495 more units per mile of fuel. And what about the y-intercept? Well, in general, the y-intercept in a linear equation is the value that the equation outputs when x is 0. So in this particular case, if the number of rail cars is 0, the model predicts that the train will need 10.677 units per mile of fuel. However, I would not trust the prediction of 10.677 units per mile of fuel when there are 0 rail cars. That's because this is an extrapolation, since we did not collect any data on trains with less than 20 rail cars. Extrapolations are in general not trustworthy. Let's talk about the properties of this correlation coefficient r. So the calculator computed that r was 0.9836. But what is correlation actually telling us about the relationship between the number of railcars and the fuel consumed? Well, first, the sign of the correlation tells you the direction of the association. Positive r means the relationship is sloped in the positive direction. Negative r means the relationship has a negative slope. So it makes sense that r is positive in this case. The correlation is always between -1 and 1. And the correlation would only be a perfect 1 if every point was perfectly on the trend line. Now, in life, there's going to be variability, so we're never going to see that. So it's only in theoretical mathematical situations that you would have a correlation of 1 or -1. Never in real life. Correlation treats x and y symmetrically, meaning if we interchange the explanatory and response variables, we would have the same correlation. Now notice in this case that doesn't really make sense because we're really interested in measuring how much fuel the train needs, so it would only make sense for us to have fuel consumption be the response variable. But there are situations where the explanatory and response variables could be interchanged. The correlation coefficient is unitless. It has no units. And it's not affected by changing the units in the problem. So for example, the fuel consumption is measured in units per mile. If we were measuring the fuel consumption in units per kilometer, that wouldn't affect R at all. This is a very important aspect. The correlation measures the strength of the linear association between two variables. It only makes sense to talk about correlation in a situation where the scatter plot looks linear. So the first thing you should do in any regression problem is if you can draw a picture, or if a picture is given to you, use your eyes. That's your best weapon. You don't want to talk about correlation unless the data looks linear. And lastly, correlation is very sensitive to outliers. A single outlier could have a massive swing on the correlation. So when we see our trend line plotted through our data here on our calculator screen, we can see that the points fall very close to the line and they're following that linear pattern, so it makes sense that r is very close to 1. What about the coefficient of determination, or r squared? Well, in general, the coefficient of determination is the percentage of the variation in the response that's explained by our model. So in this case, we could just square r, and we would get 0.967. So r squared is 96.7%. So in this context, 96.7% of the variation in fuel consumption is explained by our linear model of railcars versus fuel consumption. Now let's talk about what residuals are. A residual is the difference between an observed value and the corresponding predicted value. So an equation would be that a residual equals the observed minus the predicted. Now, we're thinking about the response variable here, so you could say that a residual equals a y value minus a predicted y value, or y minus y hat. Let's look at an example of computing a residual. From our data, we know that the train that had 47 rail cars needed 114 units per mile of fuel. Well, we could use our regression equation to predict how much fuel a train would need with 47 rail cars. So if we replaced rail cars with 47, we would find that the predicted amount of fuel that our regression equation is saying the train would need would be 111.7035 units per mile. Notice the regression equation is under-predicting the amount of fuel since the train actually needed 114. This means that the residual is going to be positive, since the actual value was bigger than the predicted value. So the residual in this case is 114 minus 111.7035, which is 2.2965 units per mile. Notice that residuals have the same units as the response variable. Now, what if we weren't given all of the data points and we were just given a computer printout such as this? This is very common in statistics questions. So the first thing you'll notice is that this computer printout, as I've highlighted in the yellow box here, tells us exactly what the regression equation is, that the predicted fuel consumption equals 10.7 plus 2.15 times the number of rail cars. But what if that was not given to us? What if that was blacked out? We could actually still write the regression equation given some of these values in the table. So let's look at this. The coefficient for the number of rail cars, the number that you're multiplying the number of rail cars by in your equation, that is the slope. So 2.1495, that's the slope. And the constant coefficient in the equation, the constant coefficient is the y-intercept. So those two values right there, the slope and the y-intercept, that's all you need to write your regression equation. Also notice that r squared is given in the table. R squared is 96.7%, and if we square root that, we can get r. Now we have to be a little bit careful because we have to think, is r going to be positive or negative? But r is positive in this case because the slope is positive and the relationship is positive. Notice that there's a standard deviation column, a t column, a p column. Those are some things that maybe we'll talk about later in the course. There's also an r squared adjusted that usually we never talk about or need for the level of statistics that we're doing. So sometimes students are confused by these tables because there's a lot more information given than you actually need to write your regression equation and analyze the scenario. Also notice they give us that S, the standard deviation for the residuals, is 4.361, and we don't really need that in this situation at all either. So that was a brief introduction to regression. I hope that has been helpful, and have a nice day.